Hello. So we are moving on to our last type of distribution that we're going to learn in this class. We've so far covered binomial distribution. Binomial distribution is this idea of either success or failure. If you pick 5 people, what are the chances that 3 of them are males? Or what are the chances that they're above this certain height? Or what's the probability that they um, have this many siblings. So it's this idea of like either they do or they don't. And this number doesn't necessarily have to be like yes or no, right? Like what's the probability that they're above a certain height? You have this like set idea of a height, but it's like either you passed this or you failed this, like negating any type of connotation with those words, negating any type of meaning that we normally hold with those words. Binomial distribution is the idea of success versus failure in trials. The normal distribution is something slightly different. First of all, we deal with continuous variables, not discrete. So continuous random variables, we're going to talk about that for a second. But it's not just all continuous random variables. It's a specific type of distribution with continuous random variables. So let's first just talk about finding distributions with continuous random variables. Your notes hopefully don't look like this. My original idea was that we were going to create the distribution histogram, and man, that just takes a really long time, and I feel like we've done it a lot, and I just don't want to. So let's not. So you hopefully should have the actual like visual representation here. I'm going to show you what I've done by hand. So your graph should look something like this. It's scaled a little bit differently. And you've got all of these probabilities. Go ahead and copy down these probabilities into your table. I'm sorry, I just had this like big idea of like, we're going to create the probabilities and then we're going to graph it. And it's a lot of work. It makes your notes longer, and that's not what we're looking for right now. So go ahead and start copying down. Realize that what you do is you take your frequency and divide it by your total sum, right? This is not anything new to find our probabilities. It's your relative frequency, or just what we understand of as probability in general. So here's what they end up being. Notice that we don't ever get above 0.2 as a probability. We don't ever get above 20% as a probability with the height of a child and their frequency. But we do go ahead and graph that. And how we're making these like distribution curves, as you can see later, is we take this idea of the histogram, we take the middle point, and then we connect the dots. If I wanted to like smooth that curve, I could smooth it over and kind of make it a little bit nicer. But this is the general idea of how you get these distributions. Continuous random variable, continuous, hey, we've got a range of values, so keep that in mind. But that's really the difference between continuous and discrete, is the fact that we're not just dealing with one number, but rather a range of numbers. We still graph it as a histogram, and when we start talking about our normal distribution curves, this is where the distribution curve comes from, is this histogram and turning it into a bell curve. When we're dealing with these probability bell curves, we're actually talking about the area underneath the bell curve, okay? So we're talking about the area of these rectangles. And if it's a length of 1 and a height of whatever this is, the area is actually representative of the probability, right? If this length down here is 1, to find the area, it's length times height, and the height is actually just a physical representation of what that probability is. So when we start dealing with this normal distribution curve, we're talking about the area underneath the curve, and that is a hint to you, for future you, to know that that's actually integral calculus, which is going to be like the final penultimate concept you're going to be learning in this class, is how to deal with integral calculus, which deals with the area underneath the curve. But you can break down the area into these rectangles, and if we wanted to find the probability between this and this, you'd really just be finding the area underneath the curve, the area of these 2 rectangles, and then adding them together. If I wanted to find the probability between here and here, I would just find the area between those 4 rectangles and add them up. So I'm just finding the total area under the curve. That's the main idea with normal distribution, is that it's created from a histogram and connecting the center points of the histogram to create this curve. And then when we start pulling out probabilities, what we're pulling out is the area underneath that curve, which is a visual representation of the probability here. That's the main takeaway that I want you to take of how do we get to a curve that looks like this. So let's go ahead. These are my notes that I've made before making this video. So let's go ahead and write down all of the things that you saw written down in my notes. So normal distribution is a specific type of continuous random distribution. And it has to have a few key parts. The main key part, the one that's like your number one clue that, hey, this is a normal distribution, besides just being told that it's a normal distribution, is that the distribution curve is symmetric about the mean. So your mean is represented on this curve. It is that center line. This is your mean, always, with normal distribution. We write it with this fancy little u that we call mu, and that's where our mean is. And a normal distribution is symmetric across that line. Always. So that's your number one clue, that it would be a normal distribution, besides just being told that it's a normal distribution. You're normally just told it's a normal distribution. A few other things that are kind of make sense if you think about it. The total area under the curve adds up to 1. Which makes sense if we're talking about continuous probability distribution, is that we know that all of our probabilities should add up to 1. If you copy down those numbers from the table above, notice I also wrote down sum equals 1. So we know that all of those probabilities have to add up to 1, which means that the area under the curve, which represents each individual probability, should also add up to 1. So your area should always add up to 1. The last thing I want you to keep in mind is that the curve never hits 0. It's an asymptote. So this bell curve is always infinitely approaching 0, but never touches it. Which means that there's always a probability that something will happen, right? There's a very, very slim chance that the height of a child, as you can see in your table above, there's a very, very slim chance that it would be above 200 centimeters, that a height of a child would be above 200 centimeters. That's insane. There is a chance, technically, there is some sort of probability that it could happen, but there's a very, very small chance. And that's why this idea of the curve slowly approaching 0 exists, is that technically at a certain point, there's no way that something's going to happen like that, but we still have to, as mathematicians, acknowledge that there's a slim chance that maybe it could happen. Okay, so these are the main things that are going to indicate to you that it is normal. We also could be told, hey, it's normally distributed, or we could be given our information like this, the X with the tilde, with the little squiggly line. We learned in our previous lesson, in our class problem that we did together, that if we had a B next, that it represents that it's a binomial distribution. If we have an N, that means that it is a normal distribution. And what's inside the parentheses instead of this idea of number of trials with your binomial distribution, it was your number of trials and then your percentage of success or your probability of success. Here, it's going to be the first thing is your mean, and then the next thing is your standard deviation squared. In other words, it's your variance. So the pieces of information that you're given is the mean and then the variance, and then this end is telling you, hey, it's normal. So those are all of the things that are given to you in this type of symbol representation. It looks really weird, but it's just saying, hey, we're dealing with probability about a normal distribution. Here's your mean, here's your standard deviation squared. Okay, here's a few other things to talk about. This is all of the different ways, I call it the different shades of normal. So these are all different ways that normal distribution can look. It doesn't always look as nice and pretty as this bell curve does. It can look really, really squished or really flattened out, or it can be shifted around. But let's talk about why does the standard deviation come into play with this? It's called the empirical rule, and the empirical rule states that when you start adding and subtracting standard deviations from the mean, you start to represent a certain percentage of the population. So the standard deviation talks about like, okay, well then like a certain percentage, majority of your people are going to be within the standard deviation. And we've talked about that a lot, that your mean represents the central tendency, a certain type of central tendency of your data. And then the standard deviation tells you how spread out your data is. But really it's saying like how much is it clustered between or around that mean. And this is your visual representation of that. Each of these lines represent another standard deviation away from the mean. So this is going to be mu plus a standard deviation. This is going to be mu minus a standard deviation. Let me zoom in there so you can see what's going on. So these are just one standard deviation away. This represents 65% of our data, always. It's approximation, but this is an approximation that is just, it's known with normal distribution, is that one standard deviation away, either positive or negative, from your mean encompasses 65% of your data. That's just something that goes with normal distribution and something you need to know. When you go another standard deviation away, so mu plus 2 standard deviations or mu minus 2 standard deviations, you're then talking about 95% of your data. 95% of your data is within 2 standard deviations, always. It's an approximation. It's always around that. But yes, that is it's always considered, if it's normally distributed, that it is a great approximation of your percentages within the mean. The last thing we're going to talk about is the third standard deviation. So this is going to be mu plus 3 standard deviations, and this is mu minus 3 standard deviations. That represents 99.7% of your data. These numbers are always held true. 65, 95, 99.7. They're numbers you just kind of have to have memorized that deal with this relationship. That within 1 standard deviation, you're representing 65% of your data. Within 2 standard deviations, you're representing 95% of your data. Within 3 standard deviations, you're representing 99.7% of your data. We use this in mathematics all the time. If students want to move into the accelerated classes in my 9th grade year, because like students are like, oh, I want to be an accelerated, what do I have to do? They have to take the final that the rest of the 9th graders my 9th accelerated students have to take. And how we know whether they're at the right place to be with all of the rest of the accelerated students is we take the average or the mean of the test, and then we take the standard deviation of the test, and we say if they're within 1 standard deviation of the mean of the final, then they're in the same like majority of the group in terms of their ability level. So mathematicians use this all the time, this idea of like, well, if you're within 1 standard deviation of the mean, then you fall within the majority. And this idea of 65% being the majority is that. So this is the main idea when you start looking up normal distribution, this graph and this idea of adding standard deviations and subtracting standard deviations, which, hey, take a second and look at this. Look at all these weird random variables. You look super smart because you are. So this is the main idea with normal distribution.